In a previous video, we looked at whether there was a solution or not to the system of linear equations that often arises in machine learning. In this video, we're going to look at when are those solutions unique. So our objectives are to first revisit the conditions when there is a solution to the system of linear equations A, W equals D, and we'll establish conditions for a unique solution, and then we'll talk briefly about some approaches to finding these solutions. So as we've seen on multiple occasions now, many machine learning problems require solving the system of linear equations, a matrix A times a vector W is equal to a vector D. Now, I'm going to express this system of linear equations in 3 dimensions where A has 3 rows and 2 columns. And that allows me to draw this and get a visual picture of what's happening. So what we're saying is AW equals D. It means that first weight, W1, times the first column of A, plus the second weight, W2, times the second column of A, has to be equal to D. And we saw before that this is equivalent to saying that D, A1, and A2 must be linearly dependent. We can test whether they are linearly dependent by looking at the rank of the matrix. So if I compare the rank of A to the rank of A with D added onto it, if those 2 ranks are the same, then there exists a solution to this problem. That's saying that D is expressed in terms of the columns of A. In other words, there's no new information in D that isn't already represented in the columns of A. Now we're going to define script A to be the span of the columns of A. The span is the set of all vectors that can be written as a weighted combination of these A. In my 2-dimensional picture, the vectors A1 and A2 define a plane. They're going to lie in a plane, and the span of those vectors are all vectors in that plane. So we're going to look at an example where A has the first column given by 2, 1, 0, and the second column given by 1, 2, 0. Now in this case, the third column of A is exactly 0, so if I were to draw a picture for these two, I would have the span of these columns would be the xy plane, because the z component is always going to be 0. So if I look at D, and I choose D to be -1, 1, 0, well, that D lies in the span of these vectors given by the columns of A, because I can write D as negative A1 plus A2. You can check that out. Negative 2 plus 1 is negative 1. Negative 1 plus 2 is 1, and 0 plus 0 is 0. Now, on the other hand, if I take a vector D tilde, which has a component that's non-zero along the z-axis, then it's not going to lie in the xy plane. In other words, it's not in the span of the vectors given by the columns of A. And because it has this non-zero component in the z, there's no way to write D tilde in terms of a weighted combination of the columns of A. In other words, D tilde is not an element in the span of A. So let's consider another example, and in this case, let's suppose that A has 3 columns and 3 rows. So the first column is 1, 1, 0, second column is negative 1, 1, 0, and third column is 0, 1, 0. And if you look at the rank of this matrix, in other words, the number of linearly independent columns, you'll see that it's only 2, because if I take the first column plus the second column and divide that by 2, I get exactly the third column. So the third column is a weighted combination of the first 2. Now we'll choose a vector D that lies in the span of these columns. All 3 of these columns lie in the xy plane again, and we'll choose D to be a vector in the xy plane, so we know there is a solution. So in this case, I've got the first column of A is the green vector depicted here, 1, 1, 0. The second column is negative 1, 1, 0, and then 0, 1, 0. D is the vector 1, 0, 0 in blue. And what we try to do when we're solving AW equals D is we're trying to write D as a weighted combination of the columns of A. So it turns out that if you look at this, you can see that, well, I could write D as A1 minus A3. So I've got my vector a1, and if I subtract a3 from that, I end up with d. But I could also write d as 1/2 a1 minus a2. So if I take 1/2 a1, that's this vector, shorter vector in green here, and if I subtract 1/2 a2, the vector in orange, I also get d. So I have two different ways of combining the columns of A to get my desired answer, d. And therefore, the solution to AW equals d may not be unique. So the condition under which there's a unique solution or a non-unique solution can be addressed as follows. Let's start by assuming there is a solution, AW equals d. So whether this solution is unique or not can be addressed by asking whether there is a vector f that's non-zero, so that a new vector w tilde, which is my solution plus f, also satisfies this system of equations, AW tilde equals d. So then I have two different solutions. Clearly w tilde and w are different if f is non-zero, and they both satisfy the same system of equations. So if this happens, if f is not equal to 0 exists, then I have a non-unique solution. But what does this imply? Well, if AW tilde equals d, this implies that AW plus AF is equal to d. Now we can take d and subtract it from both sides of this equation, and I'm going to group that with AW. So I'm going to have AW minus d plus AF has to be equal to 0. Well, since AW is already equal to d, this term goes to 0, and we see that this condition of non-uniqueness implies that A times F is equal to 0. Now, A times F is forming a weighted combination of the columns of A. We're saying there's a non-zero F for which a weighted combination of the columns of A is equal to 0. I've written that out. This is the definition of what it means to be linearly independent. If this sum is equal to 0 for some f not equal to 0, then that means that the columns of A are linearly dependent. So we see that we get a non-unique solution if and only if the columns of A are linearly dependent. Let's revisit the example that we started on the previous slide, where A is 1, 1, 0, negative 1, 1, 0, and the third column is 0, 1, 0, and D is 1, 0, 0. The rank of A is 2. You can check that there are two linearly independent columns here. The rank of A adjoined with D is also 2 because D lies in the span of these columns of A. In other words, D can be written as a weighted sum of the columns of A. And one solution we had was A1 minus A3 was equal to D. So if I take the first column minus the third column, that's equal to D. Well, that corresponds to a W being 1, so this 1 multiplies into the first column, 0 times the second column, minus 1 times the third column. So that's a W that satisfies this problem. Another solution we saw was 1/2 A1 minus A2, and if I write that out in terms of a W tilde, I find that 1/2 times the first column puts a 1/2 in this element, minus 1/2 times the second column, plus 0 times the third column. So W tilde takes this form, and I can write W tilde as my W here on the left, 1, 0, minus 1, plus this vector F, which is minus 1/2, and 1. So if I take W minus 1/2, I get 1/2, 0 minus 1/2, I get minus 1/2, minus 1 plus 1 gives me 0. And if you multiply A times F, you'll see that you get exactly 0. We can try that. A times F is going to be 1 times minus 1/2 minus 1 times minus 1/2 plus 0, so that's just 0. And then the second row of A into F gives me the sum of these three elements, 1 times minus 1/2 plus minus 1/2 plus 1. That again sums to 0. And then of course the third column is all 0, so that's clearly also going to give me 0 when I multiply it into F. And this F is not a unique vector. because I could scale f by any constant. In other words, I can make f longer or smaller. I can multiply by some number gamma, and a times gamma f is still going to be 0. So there's actually an infinite number of solutions to this problem. And that's true in general. If the solution is non-unique, there's going to be an infinite number of solutions. So let's summarize by characterizing the solutions we have to this problem, AW equals D. Well, we saw before that if the rank of A is less than the rank of A added to D, this means that D has some components that can't be described in terms of the columns of A. Then there's no exact solution to this problem AW equals D. On the other hand, if the rank of A is equal to the rank of A adjoined with D, then D can be described exactly in terms of the columns of A, and we have these two conditions. If the rank of A is equal to the dimension of W, then we're going to have a unique solution. On the other hand, if the rank of A is less than the dimension of W, then we end up with a non-unique solution because this is a scenario that we've outlined in this previous example. Well, let's wrap up with a few comments about how we solve this problem AW equals D in practice. One issue that's come up is finding the rank of A or the rank of A adjoined with D. So finding rank seems to be a fairly important problem in machine learning, and it turns out that finding rank is really best done with a computer. And even then, we're only going to be able to find approximate rank. With certain toy examples like the ones we've been using in these lectures, you can do a procedure called guess and check, where you basically are using the definition of linear independence and seeing if you can show that those columns are linearly independent. With data and a reasonable any problem of any size, you're not going to be able to do guess and check, and you're going to have to resort to using a computer. Now the same goes for finding W. In general, for the types of problems that one encounters in machine learning, you're always going to be using a computer to solve this problem, and most likely some built-in routines that solve this for you. Almost every software package has routines for solving this problem. Now, if you want to do this manually, you've probably done that before. If you have just a couple equations and a couple unknowns, you can sometimes use algebraic manipulation to isolate the individual variables, solve for one, and then plug in for the others. You can use a systematic approach called Gaussian elimination. Now, we're not going to go over that because, in general, we are going to resort to the use of a computer for any reasonable problem, and the kind of problems that you'd have to do without one are going to be amenable to simple algebraic manipulation.